Yeah, just now is a little copy of the supplementary solution to that problem we went through last period, which I made reference to. But here I've given you a solution to calculating or measuring the number of ideal trays required in the stripping section for that problem, employing the probability paper. Of course, the Xerox copy there of the second page only covers part of the paper, but it covers all the essential parts. You can buy, for example, from K&E paper specifically designed for McCabe-Thiele graphical solutions. And this is a copy of the paper. And the solution, which this is a part copy. And you see what it is, you can see almost from looking at your own copy that it's a paper that's logarithmic scale at the ends. In other words, the scale is a logarithmic and expanding scale from 50% down to 0 or down to 1/100%, and then similarly expands from 50 up to 100% on both the x-axis and the y-axis. So the purpose of it, of course, or the advantage of it, is to be able to more accurately determine the stepwise requirements at the extreme ends, where the steps become rather infinitely small on a straightforward plot. So the first page of this then explains how you obtain it, or the way I obtained it, and simply took off the data from the previous part of the solution for the composition, the mole fraction or the mole percentage of the bottoms, the feed, and the product, and the distillate, although those not necessarily needed here, and the flow rates in moles per hour. Now, if you remember that the operating line that we've been drawing on the diagram is really the representation of an algebraic equation for a straight line for the stripping section, being namely that y is equal to L over V times x minus B over V times x of B. And so you can plug those values of the liquid and vapor rates and the bottoms rate into the equation and come up with a simplified, that's not the, there must be another copy of the original handout. Of equation of the actual equation of the operating line in algebraic form. Y is equal to 5.665. In other words, I might pause to mention that illustrates that the slope for the stripping section is always greater than 1. And here it has a value of 5.66. Times x minus 0.124. So, in other words, in order to look, you can't draw a straight line on this because it's logarithmic scale. So I then assume values of x and calculate the values of y, as indicated here, and then plot them on the graph. And so that's, of course, the lower curve here is the operating line. See, it's essentially straight, but it has a little curvature to it, and particularly toward the end, it curves off right here down to the lower part. And the next part, of course, is to plot the equilibrium curve, which I did by simply taking our table of equilibrium data for ethyl alcohol and water and plotting sufficient points. But you see, it comes out to be a straight line in the lower ranges here of alcohol. Of course, up here it becomes curves and curves into the becomes tangent. If I had completed that curve and had sufficient data up here in the upper part, past the azeotrope, we'd have had a line significantly above the curve. But I didn't plot that.
What's the value?
So,
What's the value x minus 0.0124? You just have to plot that to get the y value, right?
Yeah, that's simply the algebraic value.
So when you take x, you don't need the other x minus 0.0124. That the list of numbers you've got there doesn't mean anything.
Oh, yes, it does.
What's that mean?
In the table there, I assume values of x, and then I put down the next column, x minus 0.0124,
Okay.
and then multiplying that by 5.665 gives y, the third column. Well, anyway, after having plotted, take the steps and to find out that you got about 8 steps, whereas the best estimate we had from the other plot was about 7 plus. It was a little indeterminate the last step or two. So I hope you're interested in the fact that that can be done that way. Unless there's any questions, that'll be all we'll have to say about this particular aspect. Yes, sir.
This procedure couldn't be used for the concentrated section, right?
Well, it could be, yes, very well.
Would you still get a straight line like you do in that section right there?
In reality, and from a practical standpoint, there's not much advantage in using it in the concentrating section. In fact, there's some disadvantages. It depends on where you're working in the range here. But you see, this the equilibrium curve becomes tangent to the here at the azeotrope, which is about roughly 90 mole percent. So right here you see it comes into the tangent of the azeotropic position. And so in reality, you have a little less space to draw steps graphically than you do using the conventional plot. If you were interested in calculating steps so to separate, let's say, and theoretically you could do this by distillation, you could separate the azeotrope, that is a mixture that's higher than the azeotrope, you could separate into pure ethanol and the azeotrope. This might be a good question to ask you on an exam or something. For example, if I gave you a question that if we were able to obtain a alcohol water mixture of about 98% by weight and fed that into a fractionating column capable of affecting a large degree of separation, what would be the top and bottom products of the distilling column? Well, anybody want to answer that? Somebody says that the top would be 95% or the azeotropic mixture, and the bottoms would be pure ethanol, 100%. You agree with that? Correct answer, yes. In other words, we would have to have, well, in order to do it quantitatively, the number of steps required, we'd have to have the equilibrium data in that little narrow range between about 89.4 mole percent, that's the azeotrope, or 95 weight percent, 95.5 weight percent. Up there, the table I gave you of vapor equilibrium data for ethanol water does not give any data up there, but theoretically it could be obtained if it's not already obtained somewhere. So in other words, it's simply that's simply an example of the principle we've had before, that if you have a if you have some sort of system that illustrates or exhibits an azeotropic mixture, and where it crosses the diagonal here with the XY diagram, this is azeotrope. And so in this region here, component A, as we've illustrated here, is more volatile than component B because the equilibrium curve is above the line. So you can separate any particular feed mixture in between into the more volatile material, which is the azeotrope, as the top product, and the less volatile material, this would be 100% A or B here. X of B would be this way. And similarly, if you feed a mixture of this composition into a distilling column capable of affecting good separation, what would you get then? You get the material that's more volatile as a top product, and that is the azeotrope, because if we're and the bottom product would be pure X of A, or in other words, alcohol in this particular case we're talking about, because it's less volatile than the azeotrope. So this is kind of going back to what some things we've had earlier. In other words, you can separate a mixture into its azeotrope and one of the pure components, but the pure component you'll get will be the one that's on whichever side of the azeotrope you happen to be in the composition of the feed that's being distilled. This okay? All right. Well, now, there's a few more points I would like to discuss with you about distilling columns and their operation. And in order to illustrate that, I've got another little handout here of about 5 pages, which will be the hope we can cover most of it today. Much of this material, of course, you could find in the standard textbooks if you took the time to study them, but maybe you don't do that, so I'll give it to you. I mentioned during one of the previous periods about the consideration of plate spacing, and mentioned that there are 2 considerations to be taken into account in determining a desirable or effective plate spacing. And one is the vapor handling capacity, or vapor considerations. And so here on the first page of this handout is a little table that I prepared by using some rather empirical approaches that are in 2 different textbooks. And I might say that the main consideration here in the allowable plate spacing, or for a particular vapor velocity, or saying it the other way, the allowable vapor velocity for particular chosen plate spacing, is really based on the concept of plate efficiency. In other words, these are values that would give you good operating characteristics. And if you use lower plate spacings for a particular chosen vapor velocity, well, then you would have excessive trainment, perhaps foaming, and so forth, that would be cut down the plate efficiency. So that's the standpoint here. Anyway, I've calculated there for both 10% ethyl alcohol and 95% ethyl alcohol. And by the 2 methods, A and B, and you see that although they don't agree perfectly, they're the same order of magnitude, and so one could say that appropriate vapor velocity, if you only had 10-inch plate spacing according to this method, is only about 1 to 1.5 linear feet per second. But if you increase it about 2 inches to 12 inches of plate spacing, you can essentially double it, or the allowable vapor velocities. So if you accept these figures, they aren't necessarily necessarily exactly what you'd get if you use some other parameters for calculating it, but anyway, it's I've recommended, partly on the basis of these calculations, that plate spacings in the rectifying section ought to be of the order of 12 inches minimum. And most of them from now on are built that way in the alcohol industries. We used to have much closer plate spacings, sometimes as little as 7 inches. And although they function, they don't function very efficiently, and they also operate at fairly low rates, considering the size of the column. And the tendency is to flood very easily. And so the operating rates are very limited when you have very close plate spacings. As was indicated, I think, to some of us when we went down to the field trip, and I'd forgotten about this, but Mr. Metler pointed out that several years ago I had recommended that they redesign their stripping or the rectifying column in that double unit so as to increase the plate spacing, and they did that by respacing the plates and removing them about a third or 30% of them, and so they, with fewer plates, they increased the capacity by a considerable margin, maybe 50% increase in capacity throughput with adequate separation. So that was just an example of the importance of plate spacing. Now you see, if you want to use these figures here for 10% ethyl alcohol as typical of the low alcohol separation requirements, that plate spacing of around 14 or maybe 15 to 18 inches would give you a allowable vapor velocity of somewhere between around 4 or 5 feet per second. And if you recall, 4 feet per second was the figure that we assumed in that illustrative problem that we went through last time for the stripping section, whereas we'd assumed 2 feet per second for the concentrating section. So I think these are in the ballpark, even though they're rather crude estimates of proper values. Question?
If your vapor velocity is faster with greater plate spacing, with the velocity of your feed be faster going in also? The amount of feed you can put in per hour be faster?
Let's see, now I didn't quite comprehend your question. The question was if for a greater vapor velocity, would you have a greater feed rate? Well, not. You mean for a given particular size diameter column?
Yeah, one column.
Or an existing column?
Yeah.
Well.
Like if you're
Well, it depends.
Apart,
You mean take a fixed diameter column and then respace the plates further apart?
Yeah.
Oh yes, that's the advantage of it. That's how you increase the load, by being able to operate at higher vapor rates, vapor loads, and liquid loads as well. Well, then down at the bottom, well, I might point out here that sometimes you have to, you should keep in mind, one needs to keep in mind liquid or vapor handling capacity in terms of, with respect to the tubes that conduct the vapor to the condenser, or from the top of the stripper down to the base of the rectifier. So as a kind of a empirical rule, they allow vapor velocities of something around 40 to 70 or 75 feet per second in the vapor lines. The only particular consideration there is if you have too small vapor lines and have too high a vapor velocity, where you get too much back pressure, because you do have to have pressure to push a gas or a liquid through a length of tube. There's a friction loss. And so the higher the velocity, the greater the friction loss. So you have to have a certain size so that the friction loss is not exorbitant or too much. Then here at the bottom of this page, I mentioned the liquid capacity, and turning it over here, you'll see a general discussion about this and the effect of plate spacing, or the consideration of plate spacing in respect to this. As we've already indicated, and I think we had a little handout earlier of the liquid heads in a bubble cap tray. But maybe to remind you of it, we'll draw a little simple illustration again of, let's say, here's a bead. Schematic illustration of a bubble cap tray in which we have a liquid being delivered from the tray above, and then we have an overflow here from the tray below to the tray below. And we pointed out that there's a pressure drop across the column. The pressure here at this the pressure for plate N+1, if this is N+1, has to be greater than the pressure above the tray above. And this represents a pressure drop per tray. And this is a result of accumulation of several factors, the result of which is causing this liquid, which is down here, to back up into the downcomer to some level, which is makes it balanced hydrostatically. And so the consideration here is that because we sometimes have foaming in here, for which the density of foam is sometimes considered to be roughly half of that of the liquid, but of course that depends on the kind of foam it is, but that's kind of a general rule, that the foam would be half the density of the liquid. So if you have any appreciable frothing or foaming, well, you have to have a little space here for this to break up, and otherwise it'll accumulate up on the tray above. But obviously, any factors that increase the pressure drop across the tray, such as a greater vapor velocity, greater loading, greater flow here, you have a higher liquid level, and you have greater hydrostatic pressure drop of the vapor passing through the liquid, as well as the friction through the openings. Increasing pressure will eventually cause this liquid level to build up here till it's equal to the level on the tray above. And when you have that occasion, that situation, you have flooding or priming. And so as a kind of a practical measure, the practical rule is that the plate spacing should be checked so that the pressure drop is no more than enough to raise the liquid level up to about half of the available space. So of course, when flooding occurs, why the effect of fractional distillation separation is destroyed, and so you're soon stopped. The pressure will build up through the column and show on your pressure gauge, and if you let it to continue, something's going to happen. It's going to release somewhere, and if it continues eventually, it doesn't have any doesn't blow out lower in the column. It'll eventually blow the liquid all out through the vapor escape, the vapor vent at the top of the column, and you'll have an unpleasant situation with a lot of liquid up on the cascading down through the tower. And this happens once in a while. But of course the column becomes inoperative long before that, and a lot of your alcohol would be going out the sewer out before this, very likely before this occurs. Well, in this respect, this little last two paragraphs on this page, numbered 163, reminded me of a factor that I thought I'd take a little time to mention, and that has to do with the design of trays with respect to handling the liquid. In most cases, we have, in the simplest cases, the downcomer is constituted by a tube or maybe 2 or 3 tubes like this. But there are several other arrangements which can be let's see if I can find some diagrams of this. I don't. Well, right off the moment I forgot what page this is on. Let's see. Oh, yeah. Well, I know this is too far away to show, but I'll just indicate a couple of here, so you can see. Here's a large bubble cap tray up here. I know you can't see it very well from in the back, but I'll get a little closer here. In which here they have, these are all bubble caps, and here the overflow weir is constituted by a bar or a dam across there, you see. Instead of having the downcomers project upward to form the overflow weir, where they simply are formed by this cord weir, as it's called. You can see the backside of the plate here, or possibly you can see where the flow comes down, descends on a blank part of the plate from the tray above. So it flows across these bubble caps and on down. And so here we have 3 downcomers on each tray in that particular design. And so there's various arrangements that can be used, and sometimes instead of having tubes, there'll just be a sheet that goes all the way down to the tray below. And this is rather popular now because it's somewhat easier to put in than it is tubes. Instead of having tubes, there'll just be this cord wheel, just be a sheet extending all the way down to the next tray, so that the overflow will be simply, the downcomer, the liquid flow will be simply in a segment cut off between the shell, the column, and this plate in there, vertical plate. But I wanted to show a couple more. Point out that here there's various designs that can be used as far as the flow pattern across the tray is concerned. For example, here, this first one, which just shows a circle with two smaller circles in here, represents the single tube flow across the tray and down at the next, over the next tube, into the next tube, the next one. The little shaded area indicates the relatively inactive tray area, because the flow tends to go straight across, you see. The fluid takes the shortest path it can, so out in the perimeter here you get some less effective area, sort of an inactive area, the shaded area here. And here's an example of the same situation with the 2 tubes. Then sometimes there's arrangements where you have the tubes right beside each other, but separated by a dam, so that the flow is sort of around the column down. But this creates also some ineffective areas. And there's another arrangement here where you have, it's shown here with 6 tubes around the perimeter and 1 large tube in the middle. So for one tray, you'd have the overflow, 1 large tube in the middle, and then it's spread out radially to the 6 smaller tubes and flow down to the tray below, and then those would flow back into the larger tube in the next tray below. And then this illustrates the type I just mentioned, where they have 2 overflow channels constituted by this plate in between. Anyway, there's various arrangements like that, and so I have to go back this way. And generally speaking, the tubes empty into a little seal cup at the bottom, which you have to have a certain amount of clearance between the bottom of the tube or whatever the downcomer is and the seal cup, so it can flow across the tray. Now, some 25 years ago or so, there was a wine maker here and distilling plant manager who invented what he called was the pumice handling column, or the pumice distilling column. And it was a continuous column, much in the same vein as we now use, but the idea was that in order to get all the alcohol out of pumice, they would slurry the pumice in a hammer mill, disintegrator, and be able to pump the whole mass through the column. And that was possible, and there may be a few plants that still use this, but most of them have discontinued its use. But nevertheless, one of the problems that had to do with handling all the pumice was that some of the solids in the pumice didn't cut up into didn't disintegrate very well, and particularly the fibers of residual stems would simply be separated like fibers of cotton or something like that, and it would tend to form strands that would hang up on sharp edges, such as the downcomers and the seal cups at the bottom of the downcomers, and so they'd gradually accumulate into long flowing fibers, ropes as it came about to be. So they had to shut down and take those out because they'd eventually plug up the passages. So one of the ways that they thought that they could accomplish this was to replace the conventional downcomer tubes with so-called J-type downcomers. Instead of having the tube here deliver into a cup here, which is kind of a standard procedure, and these would just be kind of sharp edges, of course, which would be places for these fibers to hang up. Why, the idea was that instead of having that, instead of having a seal cup, we'll just have what's called a J-type downcomer. And so you made the seal here by having a little leg here at the bottom of the downcomer. Well, there's nothing particularly wrong with this principle, except some people built some columns that didn't understand distillation at all. And other people, and even operators, had some mechanics come in and modify their columns in accordance with what then was a kind of a fad. And so the next page here illustrates a couple very bad examples of a homemade type distilling column. In the top of this diagram, you'll see that there's a plan view these are two different columns that this is in the same plant. And so, although this is not drawn exactly to scale, it approximately represents a geometric layout. Now look here on the left in the upper one, you see they had two J-type downcomers, and the one where the double circle represents the two represents a J downcomer. It doesn't represent two downcomers, but one J tube. So if these represent the discharge points of this, well, then and the single circles represents the overflow to the tray below. Well, first of all, you see they have a very short path to travel because they're located out here somewhere in the middle of the column. So naturally, liquid's going to flow the shortest distance. So it'd flow from here over to that one and here, and from that one over here and right down. And so you'd have a large perimeter area here that's inactive, the so-called shaded area, the shaded area here. And so it's a poor layout as far as that's concerned. And the other one is somewhat better, but it's equally poor in that they have two J-type downcomers here, but and the overflow tubes for the next tray located uniformly around the perimeter of the column. So again, you have a rather short path there to travel for the flow. But the worst part of this layout was illustrated by the two drawings below, which represents pretty accurate, pretty closely the dimensions as I measured it in this column. The one on the left is about 60 inches in diameter, and the plate spacing was 15 inches, the overall spacing. But this J-type downcomer was, as I shown here, located 7.5 inches away from the perimeter. And the discharge level of that tube was only 5 3/4 inches below the tray above. So what's the matter with that? Why would that be bad? Yeah, so in effect you only have 5 3/8 inches of plate spacing, because you've got to have a higher liquid level. You got to have the liquid level, or the liquid level is going to be above the liquid rise, and the downcomer is going to be above the point of discharge, and the point of discharge is only 5 3/8 inches below the tray above. So in effect, you had a 5.38 inch plate spacing instead of 15. So the column flooded very easily. And the next one is a similar situation, except that it wasn't quite so bad. And some people, I don't know whether this particular plant did it, but some people had this kind of a problem, so they thought, well, the holes aren't big enough. These are perforated trays. This is stripping section, perforated trays. So they went in there and they drilled out the holes bigger from the normal they should be about 5/16 inch. It can be a little slightly larger, sometimes lower, depends on how coarse the soluble solids need to be that have to be handled. But I visited one place where they're having a terrible problem with loss. Couldn't get any efficiency in the stripping section. And, so I looked in it, and they drilled out the holes till they were, I think, either 3/4 inch in diameter or nearly 1 inch in diameter. Well, what happened was that they let liquid get through all right, but they all went down through the holes, and nothing was going down through the downcomers. And that constitutes what you call a shower tray. If they're properly designed, then you can get a bit of efficiency by a shower type tray where the liquid is cascading down in bubbles and the vapor passing up through, but it's a very poor design. And so they had big problems with that. They had to tear it out. So, with that brief reference to those problems, in other words, I've recommended several times to producers to, when they wanted me to come around and can criticize or recommend on their columns, that to cut off those J-type downcomers, replace it with a straight tube, and in many cases that very simply solved their problems of being able to handle a reasonable load and effective stripping. You have a question?
No, I was just curious. There's enough pressure that no more liquid comes down through with a 5/16 hole. The liquid stays.
Oh, well, I haven't really dwelt much on this question of hole diameters, but the whole concept or the principle of a functioning of a sieve plate is to balance the tendency for the liquid to run through the holes against the pressure drop occasioned by the vapor passing through the holes. And also the surface tension enters in here too. If you have small enough holes, water which has a high surface tension, and particularly if it doesn't wet the plate very well, it won't run through very well. But something with a lot lower surface tension will run through small holes. So the size of the hole is somewhat important, have to be calculated or estimated in terms of the surface tension of the fluid to be handled. But the smaller the holes that you can have, the more flexible arrangement you have, because if they're quite small, and sometimes they've been made as small as a 1/4 inch diameter, but they won't. That small hole will not really satisfy the requirements in the alcohol industries very well, where you have particles that may plug the holes at that small size. So, but anyway, as you increase the size of the holes, you have a less wide range of vapor velocities in which you can operate without the liquid dumping through the holes. And obviously, if you had a great large holes, you almost it's impossible to get sufficient vapor velocity to keep the liquid from flowing down through the holes. So anyway, the typical range that's used of perforated perforations would be somewhere between 3/16 up to about 5/8. That'd be about the largest that would be recommended for the alcohol industries. That's the figures I remember. That'd be the hole diameters. And the whole area, the perforated area, somewhere between 6 and 10% of the plate, of the overall plate area. 6%, I think, is more common by at least one of the manufacturers in California. Well, if we have a few more minutes, I want to talk about a couple other aspects and that has to do with preheating the feed and heat economy. Now, naturally, we like to preheat the feed material to a column because we can save energy, save steam. And as we've seen, in our McCabe-Thiele problems, the temperature has some effect on the ease of separation too. But nevertheless, from the standpoint of pure economy, it'd be desirable to get as much heat out of that stillage as possible. And so in the conventional manner, the feed is run in the wine industry. The feed wine entering the system is run through some type of heat exchanger. The ones we saw down there at Bear Creek Winery were simply a series of concentric tubes in which the feed ran through the center tube, and the stillage going out of the base of the column flowed through the annular space between the inner tube and the outer tube, and so you reached a preheat temperature of maybe 140 to 150, I believe they said, degrees Fahrenheit. And of course, that means you could calculate what the temperature would be of the discharged stillage. It would be quite a few degrees less than came out of the bottom of the still, but it still have a lot of energy in it. In other words, assuming that the feed rate was approximately equal to the stillage rate, and that you had to provide 60 degrees of preheat to the feed, you'd have about 60 degrees drop of the temperature of the stillage from about 212 down to, what would that be, 160 from 21, 6 from 21 would be 150, 150 or 155 degrees. Well, that still has potential energy that might be used. So there's two devices that are in use in California. And the first one is a little drawing here called Distillation Economizer. And it makes use of the principle of what we call thermal compression, or recompression of vapor. If you look at the diagram, you'll see at the base of the distilling column, the liquid would flow out there through that little dotted line, through the float tank, and up into the middle part of this little chamber here where the valve is shown. And this upper chamber here would have this stillage flowing into it. Now the high pressure steam coming from the boiler, which typically is usually no less than 150 pounds per square inch, is considerably higher pressure than has to be to provide heat energy and flow into the still. where the base pressure is no more than 3 to 4 pounds per square inch, usually at the maximum. So what is done here is this high pressure steam is allowed to expand through a orifice or a venturi type tube, where it gives up pressure energy and is converted into velocity energy. So when you go through a small orifice, the energy that's necessary to increase the velocity is obtained at the expense of the pressure energy. So you lower the pressure. And so if that's in contact with this hot stillage, you can, in other words, you can reduce the pressure down to where you get a partial vacuum in a chamber like that by passing the steam energy through it. So this is sufficient vacuum to cause some of this stillage, the liquid in the stillage, to flash into vapor form, essentially steam. Now, the little dotted line I inserted in here myself is up at the top of this chamber, so any liquid flashed off the stillage flowing into this lower part of the chamber then is brought down, drawn into this steam flow, and then as it passes to the open part of this venturi, or the constricted portion, it is compressed, or in other words, it's mixed with it. So you get some amount of the vapor then, some amount of the heat energy transferred from the stillage into the steam. And the claim is that properly operated and installed, you can save about 25% of the steam requirement by this technique. Yes?
Did you just say, first I thought I heard you say that the steam energy went to the stillage and made the stillage vapor. And then I thought you went and you said that the stillage that you just made into vapor made water into steam again.
Well, let me go through it again. Let me go through it very briefly again. The action of the expansion of the steam causes a pressure drop in this chamber, which causes some of the liquid in the stillage, essentially water, at the boiling point, to flash into a vapor because you lower the pressure below the operating pressure. And the amount of steam that's created then, or the water vapor by evaporating stillage, is mixed with the main stream of steam from the boiler and enters the base of the dripping column as the heat energy or the vapor for the operating the still.
This vapor liquid separator is where this goes on, right?
Yeah, that's what it is. Mm-hmm. Initially, when I got a copy of this, I couldn't understand how this worked very well, but I talked to Mr. Nallum, who's a designer of drew this drawing not too long ago, and he pointed out that they didn't show in the drawing this tube that rises up to the top of that separator chamber, and because it's inside. So I've shown here the dotted line. So that's where the vapor escapes from the liquid and mixes with the steam. And this is the principle called vapor recompression. Now the discharged stillage, although it will be somewhat lower temperature than it would be if you didn't have this economizer apparatus attached here, still would have enough heat energy though to give up considerable amount of preheat temperature to the incoming wine through a conventional preheater, conventional heat exchanger. So that's the principle they use here. Now, on the next page is a little sketch here of the top part of that is really what I've been talking about. Maybe it's a crude sketch, but it might have been a little clearer if we'd have been referring to that. Vapors flashed off the hot stillage and recompressed in the thermocompressor to effect some economy in the steam requirement. The partially cooled and slightly more concentrated stillage is then used to preheat the feed in a usual heat exchanger. And I've shown here a little schematic drawing over here on the left of a conventional heat exchanger. But then in parentheses I put down here, however, the final volume of the stillage would be the same as if no thermocompressor or heat economizer was used, because the amount that this stillage is reduced here in volume by vaporizing some of the steam is compensated by the increase in amount of steam that goes in in the form of vapor. Now down at the bottom here is a little drawing of a rather interesting principle utilized by, I might as well mention the names because you'll all see it sometime, is the large distilling column located at United Vintners plant in Madera, California. It's a very tall stainless steel column, which I think I referred to before. The stripping column here is, according to my notes, is 10 feet in diameter. The rectifying column on the top of it here appears to be about 8.5 feet in diameter if it's drawn to scale, and has looks like about 70 plates in it, 70 trays in the stripping section, and 20 trays in the rectifying section. Has 70 trays in the rectifying section and 20 in the stripping section. But anyway, one interesting feature about it is a preheating method. It's a preheater, which is located over here. It's a rather large type of apparatus, but it is a method of preheating the feed by, again, flashing off vapor from the stillage, where this vapor is mixed directly with the feed. So now if you refer back to this little sketch here, maybe we can get the principle. Stillage flows out here, the bottom of the stripping column, and into the bottom of this preheater device. And space above that is opened up to the upper part of the chamber, where the feed goes in and cascades down through some perforated trays. And cascades down is collected in this lower conical portion of the apparatus. But at the same time, up at the top of this is another one of these vapor recompression devices. And so the high pressure steam from the boiler is allowed to expand again, reducing the pressure laterally to the direction of flow, and creates a partial vacuum, which then causes some of this stillage to be flashed into vapor, and it goes up here and then mixes in a kind of a cascade arrangement, a shower type column if you want to think of it that way. And the feed, of course, being a lower temperature than the vapor, condenses this vapor. So in this case, the flashed off liquid actually mixes directly with the feed and has the effect of diluting the feed.
So it's liquid plus vapor.
But in other words, the flashed off vapor does not enter the steam line as it does in the previous case, but enters the liquid, and so causes a dilution of feed. So I thought maybe you might be interested, and I see that bottom note there. I said sometime I'm going to calculate some conditions for the same feed rates and steam, but I guess I never did that. At least I don't have the results here. Which page? The last page?
No, right at the bottom.
Yeah. It's under vault and it's full down. It's right.
The statement, it reads, the vapor is flashed off the hot stillage, but mixes directly with the feed to provide a preheat temperature increase. Well, or an increase in the feed temperature, you could say it better maybe. The effect is to dilute the feed. A little bit.
Now the steam that's going in to heat the column, this is liquid coming in from the feed, plus vapor that's being flashed up. So what's being sucked up in that vapor compressor is a combination of liquid and vapor?
Actually, about the only action of the vapor recompression here is to provide a partial vacuum, and no vapor passes on up into the
Nothing is taken up.
well, maybe a little bit, but in fact, if it's operating the way it's designed, the vapor flashed off the stillage mixes with the feed directly and is condensed. But this chamber does operate under a partial vacuum, you see, in order for it to function that fashion. Okay.